intrinsic velocity, or how the speed can exceed the intrinsic speed or speed of light. Let us see the explanation. To see that explanation, let us consider the phase. Don't consider the wave. We'll consider the phase, because phase velocity we have found out as the velocity of the phase, not the velocity of the wave. Remember this. It is not the velocity of the wave, it is the velocity of the phase. So consider the phase, not the wave, which is propagating along the z-axis. So I'll consider that. So phase front, if the phase we are considering the phase along the z-axis, then the phase front will be perpendicular to the z-axis. Therefore, it will be in the xy plane. Since it is propagating along z-axis, phase front will be along the xy plane. So, if it is along the xy plane, then we can write the electric field as E is equal to E0 exponential j x beta cos phi x plus y beta cos phi y into exponential j g beta cos theta. Why we have divided it into two parts, that will be clear now, because we have taken it is propagating along z direction. The phase is propagating along z direction. So phase propagating along z direction, that we have separated out. So exponential j z beta cos theta, that is the phase propagating along z direction. The rest of the part is the phase in the xy plane. Exponential j x beta cos phi x plus y beta cos phi y, that is a phase in the xy plane. So phase part we have taken. This phase part is moving with phase velocity in the z direction. So let us see that pictorially. Look at the picture given below. The dashed line, if you look at the dashed line, PAB, that dashed line, the first dashed line, which is near the origin, PAB gives you the phase front. That is in the xy plane, that is moving. And that is crossing the z-axis at the point A. PAB is the wave front. It is moving along the orange line, the orange arrow that shows the direction of the propagation of the wave. Phase front is PAB, that is the cross section of the phase front, that is PAB. Now it is crossing the z-axis at the point A. Then it moves along, the phase front moves along the orange line. So P has moved to the point P dash, A has moved to the point A dash, B has moved to the point B dash. So that is the second instant. In the first instant, it was at PAB, it was crossing z-axis at A. In the second instant, it is crossing z-axis at the point B dash, not at the point A dash. The point A has moved to the point A dash, and point B has moved to the point B dash. Now you can see from this, what you can see is P has moved to the point P dash, which is the propagation of the wave. Wave has propagated, so P has moved to point P dash, A has moved to the point A dash, B has moved to the point B dash. Now in this, the interesting part is, along the z-axis, A has not moved to the point A dash, but A has moved to the point B dash. So A and B dash, they are in same phase. Their phase remains constant, not A and A dash, but A and B dash, their phase remains constant. Look at that angle, the triangle A dash, B dash, or A, B dash, that triangle you can consider. There are two triangles, you can consider any of these two triangles. Both these triangles are right angle triangles. A dash, B dash is a right angle, A, B dash is a right angle. Then the side in front of that angle, that right angle, is AB dash. That AB dash is greater than A dash or B dash. A dash is equal to B dash. Now what is the velocity? Velocity of the wave will be A dash, that is the distance, divided by time. a dash by t or b dash by t. Both these are equal because a dash is equal to b dash. Because p a b and p dash a dash b dash, these are two parallel lines. Therefore, a dash is equal to b dash. So a dash by t is equal to b dash by t. That is the velocity of the wave. Wave has moved from, because wave front is p a b, and wave front next instant wave front is p dash a dash b dash. So a has moved to a dash with a velocity. So that velocity will be a dash by t. But the phase has moved from a to b dash, so it will be a b dash by t. Now a dash is smaller than a b dash. Therefore, a b dash by t will be larger than a dash by t. So the phase velocity will be larger than the velocity of the wave or the intrinsic velocity. So this you can see pictorially. So the phase, as I have told you now, let me put it in perspective. Phase varies in the xy plane. It propagates along the z-axis. Now it is obvious, as the wave is not propagating along z-axis. Wave is propagating along the orange line. So when p moves from p to p dash, at that point a moves from a to a dash, b moves from b to b dash. A and b dash are in the same phase, but a b dash is greater than a dash and b dash. Since on this they are greater than a dash is greater than b dash, therefore you can say that the phase velocity is greater than the given velocity v0, the velocity of the wave, or the velocity with which the wave is propagating from the phase velocity is greater than the velocity with which the wave is propagating. So that we can say. So now with that we come to the end of phase velocity. We have seen now that phase velocity is not the velocity of the wave, so therefore it is not a physical velocity. That is one point that we have seen. And the phase velocity is always greater than equal to the velocity of the wave. Now we have seen when it will be greater than, we have seen how it will be greater than the velocity of the wave. When it will be equal to the velocity of the wave, we say that the phase velocity is greater than equal to the velocity of the wave. Now greater than we have justified. Next question comes, when will it be equal to the velocity of the wave? Now if you put this orange line that I have shown, if we move that towards the z-axis and align it with the z-axis, then the wave will move along the z-axis and the phase also will move along the z-axis. In that case, that is the only case in which these two will be same. So when the propagation of the wave and the propagation of the phase are along the same axis, then phase velocity will be equal to the velocity of the wave. That is the condition under which it will propagate, and they will be equal. Otherwise, the phase velocity will always be greater than the velocity of the wave or intrinsic velocity. Phase velocity is always greater than intrinsic velocity. It is not the physical velocity of the wave. And with this, we come to the conclusion on the concept of phase velocity. Then we'll come to the next concept, which is called the group velocity. For the group velocity, we start with V0, which is the velocity of, or V0 is the intrinsic velocity. And what is V0? V0 is the velocity of all the points on the phase front or on the plane. If we are considering a plane wave, then all points on the plane that contains the electric field and magnetic field. So the plane that contains E and E tilde and V tilde, or E and B, on that plane every point is moving with a velocity v0. So v0 is the velocity of the group of points on the plane PAB or P dash A dash B dash, or if you keep on moving on all those points. So group of points on the plane that contains the electric field and the magnetic field is the velocity, intrinsic velocity v0. Now this velocity will have components along the principal axis x, y, z. This intrinsic velocity v0 will have components along the principal axis x, y, z. How to find out what will be the components? As you know, if it is propagating with velocity v0, then its direction will be along the direction of this velocity v0 will be along the direction of the propagation of the wave. And the wave propagates, its vector is unit vector of the wave, propagating wave is n cap, which is equal to x cap cos phi x plus y cap cos phi y plus z cap cos theta. Therefore, v0 will also have components along x, y, z. So since it is the velocity of group of points, we call it the group velocity. So along the x-axis, the component will be Vgx will be equal to V0 cos phi x, where phi x is the angle made by V0 with the x-axis. Similarly, Vgy will be equal to V0 cos phi y. Phi y is the angle made by V0 with the axis y. And Vgz will be equal to V0 cos theta. Theta is the angle made by V0 with the z-axis. Now if you look at this, all these have no denominator. They have in the numerator a multiplication of cosine function. Now cosine function, as I have told you, cosine function has a minimum amplitude of 1 and minimum amplitude of 0 and maximum amplitude of 1. So when cosine function is 0, then these components will be equal to 0. If cosine function is maximum, these components will be equal to V0. Maximum means 1. So if the cosine function is 1, then these components will be equal to V0. Therefore, the components will vary between 0 and V0. So 0 will be less than equal to the components which are Vgx, Vgy or Vgz, and that will be less than equal to V0. So this is the limit on the group velocity. So we have discussed about the limits on the phase velocity and limit on the group velocity. So we have seen this. Now when Vc is equal to 0, what does that imply? Vg is equal to 0, what does that imply? Vg is equal to 0 implies that there is no propagation of energy. Absolutely no propagation of energy. Since Vg is equal to 0, which means the wave is not propagating, wave is static. Vg is equal to 0 implies that V0 is equal to 0, so the velocity of the group of points is 0. So the plane is not propagating, plane is static, which means there is no propagation of energy. So Vg is equal to 0. When Vg is equal to 0, that indicates no energy propagation. Now, second point is the important point. Second and important point is what is, we have seen what is VPX. VPX is equal to V0 by cos Px, and VGX is equal to V0 by cos Px, V0 into cos Px. Now, in both these cases, there is a common limiting term. VPX, its limiting term is upper limit. VPX, the lower limit is V0, whereas VGX, the upper limit is V0. Right. So if I draw it on the axis, V0 will be, if I draw the velocity on the axis, one side, the top of the axis moves towards infinity, bottom of the axis moves towards 0, then there will be a point which is equal to V0. There will be a line which is dividing Vp and Vc. Vp will be greater than V0, greater than equal to V0. Vg will be less than equal to V0. And they will meet exactly at V0. Under what condition they will meet, that you will see that Vp and Vg, they meet only under one condition at one point, which is Vg, when it is propagating, the direction of propagation is equal to one of the principal axis. Then they meet, then it becomes V0. And under that condition, you can see Vgx is equal to V0 cos Px, Vpx is equal to V0 by cos Px. Therefore, their product Vpx into Vgx is equal to V0 cos Px into V0 by cos Px. Cos Px in the numerator denominator will cancel out. V0 will be multiplied by V0, giving us V0 square. So Vpx into Vgx is equal to V0 square. Similarly, Vpy into Vgy will be equal to V0 square. Vpz into Vpvgg will be equal to V0 square. Therefore, we can say Vg into Vp is equal to V0 square. So the product of group velocity and phase velocity is equal to square of the intrinsic velocity. That is what we can easily say. This is the relationship between intrinsic velocity, group velocity, and phase velocity. So with this, we come to the end of the concept of group velocity, concept of phase velocity, and the relationship between group velocity and phase velocity. Now we will conclude today's lecture with some discussion on the wavelength. So, wavelength we have already defined. Lambda is equal to 2 pi by k, that we have defined. So lambda is equal to 2 pi by k. That we can write as 2 pi by, for k, we can write from dispersion relation, k is equal to omega by V0. So lambda is equal to 2 pi by omega by V0. Now V0 take it to the numerator, so that gives us 2 pi V0 by omega. Omega is equal to 2 pi f. So 2 pi in the numerator and denominator will cancel out. If they cancel out, then that lambda is equal to V0 by f. So this is a relation, well-known relation. We just derived it. So lambda is equal to V0 by f. Now, how we can find out what will be the components of lambda along the axis. So lambda x will be 2 pi by kx. So that will be 2 pi by k into cos 3x. That you can write as V0 by f cos 3x, or that we can write as lambda by cos 3x. It is simple, since k over 2 pi by k cos 3x. For k we can write V0 by f, f by V0. So that will give us V0 by f cos 3x. So then V0 by f is equal to lambda. So that we can write as lambda by cos 3x. So lambda x is equal to lambda by cos 3x. Similarly, lambda y will be 2 pi by ky. That will be lambda by cos phi. And lambda z will be lambda by cos theta. So now we see that lambda x is equal to lambda by cos px, lambda y is equal to lambda by cos py, lambda g is equal to lambda by cos theta. Again, as in case of phase velocity, in case of wavelength also we see lambda x, lambda y and lambda z will be greater than equal to lambda. So the limit will be on lambda x, lambda y, lambda z. The limit will be, they will be greater than equal to lambda but less than equal to infinity. So lambda is less than equal to lambda x or lambda y or lambda z. That will be less than equal to infinity. So this is about the wavelength. So wavelength and the components of the wavelength. So if the wave is propagating in any arbitrary direction, then its component along the principal axis will always be greater than the wavelength of the wave. If it is propagating along one of the principal axis, then that component will be equal to the wavelength along the principal axis. So with this, we come to the end of the concept on the plane wave. If you have any doubts, please ask me, or if you have any comments, you can make the comments. Please, we can have some discussions today.